In this talk, I'd like to highlight a little of the diversity we expect to see as we start to probe the characteristics of planets outside our solar system. This talk is based on a book that was published in the AAS IOP ebook series this time last year, which gathered 5 teams to look at the upcoming exoplanet observations and the potential diversity we might see in planetary magnetic fields, the planet heat budget, composition and volatile abundance amongst rocky planets. Overall, the book asked, what is a planet's environment when it's not quite Earth? The reason this question is so key is that we have now discovered over 4,000 planets outside our solar system, many of which have sizes that suggest they may be rocky. A number of these have been discovered to orbit in the so-called habitable zone, which is the region around the star where a planet like the Earth could support liquid water on the surface. So, if a planet like the Earth is out there, then we will find it in the habitable zone. This is obviously exciting for astrobiological studies, as not only is our planet the only world we know that is habitable, but life is likely to be much easier to detect if it formed and evolved in an environment similar to our own. However, even if we did detect a planet capable of supporting life in the habitable zone, it is unlikely to be identical to the Earth. There are too many parameters that could change, such as radius, mass, the stellar type of the host star, the composition of the planet-forming material, and the formation history of that world. So, what do these shifts do to the planetary environment? Do they produce planets that are recognisably Earth-like, with the same abiotic and biological signatures as our planet? Or do they create very different worlds, where the geological and chemical processes create very different detectable signatures? This information is going to be vital for understanding planet characterization data from instruments such as the Webb telescope. Exoplanet science is now moving from an era of detection to characterization, where for the first time we will be probing properties that directly relate to conditions on the planet's surface. However, this link is not going to be straightforward. For example, one of the main techniques that will be the focus of the next decade is transmission spectroscopy. Here, light from the star is detected after it passes through the planet's atmosphere. Molecules in the atmosphere absorb particular wavelengths, like a Pac-Man. By observing which wavelengths are absorbed, we can discover the molecular content of the planet's upper atmosphere. However, deeper in the atmosphere and closer to the surface, the higher pressure causes the atmosphere to become opaque to all wavelengths, so we only get an inventory of the planet's upper gases. This is content that will be the combination of all planetary processes, from the internal mantle and core dynamics, surface and atmospheric chemistry, and, if it's present, the hint of life. To pick out that biosignature, we therefore need to understand all the abiotic processes that go on in the planet. This might be relatively easy if the planet is identical to Earth, but how do those abiotic signatures change as we shift from the Earth's properties? Let's take the Earth and cut it like a cake. Moving from the inside out, we can have a look at a few of the properties we don't expect to be constant as we move to another star system. Let's start with the core. One of the processes we most strongly associate with the core is the generation of the planetary magnetic field. Perhaps ironically, as the magnetic field is generated at the deepest point in the planet, we notice its influence most strongly several atmospheric scale heights above the surface. Because the magnetic field strongly influences the motion of the charged particles that exist at these heights, it influences atmospheric loss, and therefore has a big impact on surface conditions. As an example of how the magnetic field can affect atmospheric loss, Dong et al. Performed simulations of TRAPPIST-1e. The TRAPPIST-1 system comprises of 7 Earth-sized planets orbiting a red dwarf star, 4 of which are in the habitable zone. Dong et al. Found that if TRAPPIST-1e possessed an Earth-like atmosphere but no magnetic field, then the loss rate of oxygen ions was about 4.7 times 10 to the 28 per second. This is nearly 5 times higher than the magnetized case of about 1 times 10 to the 28 per second. Notably, both values are a lot higher than the Earth's estimated loss rate of 1 times 10 to the 25 per second, demonstrating also the importance of the host star type. So how likely is a planet to generate a magnetic field? In the terrestrial region of our solar system, most of the planets show evidence of having an internally driven field at least at one point in the past. The exception is Venus, which does not currently have a magnetic field and whose past is a mystery. The basic requirement for a magnetic field is to have a large quantity of electrically conductive fluid that is cooling at a rate that can drive convection in the core. This means that larger planets such as super-Earths may be expected to have large dynamos if their core size scales with the planet size. Quantitatively, the magnetic's Reynolds number is proportional to the length scale of the dynamo generating region, in this case the planet core. However, the non-magnetic elephant in the room is obviously the solar system's other Earth-sized planet, Venus. Exactly why Venus does not have a magnetic field today is not known, but one idea was proposed by Jacobson et al. In 2017, who suggested that the core of Venus may be compositionally stratified. A stable set of layers could form naturally during accretion while the planet was forming, as more lighter elements would enter the metal as the planet grew and pressure increased. This stratification throttles convection and prevents a dynamo. A similar stratification would also have occurred on the Earth, but a giant impact, such as when the Moon formed, may have disrupted this and allowed the core to mix and convect. If this is true, then the presence of a moon may be one of the hints that a magnetic field could have been generated. As we step out from the core, we reach the planet mantle. Sandwiched between the hot planet centre and the cold surface, the mantle convection drives the interior planet dynamics and governs the planet's long-term evolution. Heat loss through the mantle controls surface properties such as volcanism, and so the planet's atmosphere, and the recycling of volatiles and nutrients between the surface and the upper mantle. If the mantle stops convecting, the planet would become still and dead. Sources of heat that power the mantle include radioactive isotopes that are gathered into the planet during its formation. Uranium-235, 238, potassium-40 and thorium-232 have long half-lives that can power the planet over its evolution. A second source is heat from giant impacts during accretion. Both of these are expected to differ between planets, with stellar abundances of radioactive isotopes showing differences of a factor of 2, and accretion being a fundamentally stochastic process. The surface is always expected to be cold relative to the interior, which is true even for a planet like Venus. However, the rate at which heat is lost will depend on the structure of the lithosphere that forms the planet crust and top part of the mantle. This may be mobile like on Earth, whose lithosphere is split into plates, or it may be stagnant like on Mars, or possibly in between like Venus is suspected to be. The heat budget team in our diversity volume put together a simple model based on scaling laws to estimate the movement of heat through planets with slightly different properties. A mobile lid lithosphere allows the planet to cool much quicker than a stagnant lid, and, all things being equal, a larger planet has a more vigorously convecting mantle and larger heat flux, due to the higher density and gravity. However, a major factor in determining the heat flux is that of mantle viscosity, which depends partly on the planet composition. The Earth's upper mantle consists of olivine, but on a more silicon-rich planet, this might become orthopyroxene, which has a lower viscosity than olivine. Alternatively, it might become clinopyroxene, whose higher viscosity could hinder convection and potentially stop the mobility of the surface. The composition affects density, which is often measurable from observations that give the planet mass and radius. However, density alone is not enough to pin down the composition. For example, the TRAPPIST-1 system has some of the most accurate measurements of any rocky exoplanets, with the radii known to within 3%. Yet the composition of these planets can be fitted with very different choices. Their low densities could be explained with either a large amount of water, amounting to 40 to 200 Earth oceans worth, or a small core. This can be seen more clearly if we plot the mass and radius of 53 approximately Earth-sized exoplanets. The green line marks an Earth-like composition, while blue gives a water-rich composition and red gives one heavy in iron. The planets lie scattered between these compositions, and adding the error bars to the measurements shows that the mass and radius is not enough to discern the planet makeup. However, a hint may be found in the stellar composition. As planets form out of the dust and gas that also forms a star, their non-volatile abundances should reflect the star itself. For this, the Hypatia catalogue is an incredible resource, with data for nearly 10,000 stars, nearly 2,000 of which host planets. The catalogue shows the main rock-forming elements of magnesium, silicon and iron vary within about a factor of 2 of that of our Sun. It's not a huge variation, but it's enough to produce some very alien compositions. For example, stars with carbon to oxygen ratios greater than 0.8 may host sufficiently carbon-rich systems that carbon replaces silicon in rock. Calculations by Unterborn suggest this would produce a mantle of graphite and, as the pressure increases, diamond, whose high viscosity would squash mantle convection and prevent a mobile lid. Once the planet's bulk composition has been determined, we reach the volatile inventory. As volatiles are normally in vapour form in the habitable zone of stars, they need to be delivered to the planet from elsewhere in the system. A major consideration for this delivery is the location of the snow line, which is the point where water can freeze into ice and become a more packageable entity to deliver to rocky bodies. The distance of the snow line depends on the stellar type. Planets around late-type stars like M dwarfs have snow lines further from the habitable zone, whereas early-type stars have the two regions much closer together. It may therefore be easier to get water into the habitable zone of earlier-type stars. Another factor is the planet architecture. Work by Morbidelli and also Dash suggests that Jupiter was able to set up a pressure trap that stopped large particles entering our habitable zone. If so, our habitable zone may be far less water-rich than if the giant planets had not been there. Then, of course, planets may not stay on their original orbit. While still embedded in the planet-forming disk, young planets experience a force that can change their orbit. This migration may take the planet from outside the snow line into the habitable zone, bringing with it a high water content regardless of the relative distance between the snow line and the habitable zone. By mass, the Earth only has about 0.02% water. Boost this and the planet environment may change. During the early formation of the planet's surface is expected to be largely magma. As water and carbon dioxide lower the melting temperature, a higher abundance of volatiles may prolong this phase. After this, a large amount of water may produce a global ocean. While water is essential for life, too much water can present a problem for the planet. The added weight of such a large ocean may prevent surface melting and suppress volcanism, limiting habitability prospects. So going back to our original question, what is a planet's environment like when it's not quite Earth? When compiling this book, I felt there were 3 messages in particular that kept reappearing. Firstly, small changes in size and composition can strongly affect planetary processes. Also, observational clues to these changes can be found in the properties of the system, such as stellar abundances and planetary architecture. This information will be essential to understanding the atmospheric data from the planet. Finally, more experiments and theoretical work are needed to explore the impact of changes to the Earth's composition. Without this, we risk misinterpreting an abiotic signature for a biological one, or the reverse. This book was designed to highlight the kind of considerations needed to understand planet diversity, but is just a start to set the scene to this new era of planetary exploration.